Instead, it just needs to tell the control unit how the two numbers compare to each other. For this, the ALU uses what are called flags, and they help the control unit decide what to do when it receives the next instruction, like jump if, which we'll see later. For now, though, let's say that we are working with an instruction that does produce an output. Where does that output actually go? Well, the 8 wires coming out of the ALU would actually run to what is called a register. A register is a very simple component whose only job is to store a number temporarily. Registers act just like RAM, except they are inside the CPU, making them faster and more useful for storing a number temporarily while an instruction is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register's set wire. The set wire is just like the one we saw earlier for RAM. When the set wire is turned on, the register saves whatever number is on its input wires. Once we have the output saved in the register, though, how do we get it back out? Well, when we are ready to move a number out of the register, we need another control wire called the enable wire that also runs from the control unit to the register. As soon as the control unit turns the enable wire on, the register will output whatever number is saved inside. The output wires of the register then connect to what is called the CPU bus. A bus, as we saw earlier on the motherboard, is simply a group of wires that connect multiple components inside a computer. On the bus are some other registers with their own set and enable wires. These may have numbers from previous instructions already saved inside. So the control unit will then turn on the set wire of the particular register that it wants to save that number to, and that number will be saved in that register. Afterward, the control unit will then turn off the enable wire from the first register and clear the bus. The 4 registers at the top are just used for storing numbers between operations, so they have output wires that go directly back onto the bus. So now we have moved a number from one register to another just by turning some wires on and off. That's the advantage of the bus, easily moving numbers between components. The disadvantage of the bus is that you can only have one number on it at a time. Because of this limitation, the arithmetic logic unit uses a temporary register for input B. When the control unit is processing an instruction involving the ALU, it will move one of the inputs to the temporary register. The temporary register has no need for an enable wire since it only outputs to the ALU and doesn't conflict with any other registers. The other input to the ALU comes directly from the bus. The control unit will enable another register, and that number will become input A to the ALU. That number stays on the bus until the ALU is finished processing the instruction. And so now there are 2 inputs to the ALU, and we're ready for the ALU to perform an operation. As we saw earlier, the control unit knows what operation to tell the ALU to perform because of the instruction it receives from RAM. The instruction itself is in another register called the instruction register. By the way, the input wires from the bus won't affect this register since the instruction was already saved in a previous step. This register, like the temporary register, also has no need for an enable wire since it just outputs to the control unit. Based upon this instruction, the control unit then tells the ALU what type of operation to perform. So let's say the instruction we're processing is a compare instruction. With the compare instruction, we're not interested in the number that is output by the ALU. We only want to know how the 2 inputs compare to each other. For that, we use the flags that we talked about earlier. Each flag is just a wire that turns on or off depending upon whether or not a certain condition is true. Inside the Scott CPU, there are 4 flags, and we'll look at 2 of them now. The A is larger flag will turn on if input A is larger than input B. If the inputs are the same, then the equal flag turns on, and if both of these flags are off, that means input B is larger. But in this case, the equal flag is on, so that means both inputs are the same. Once the compare instruction is over, we still need to use the flags for the next instruction, so we'll save them to a register that only has 4 inputs and 4 outputs, 1 for each flag. Once the flags are set into the flags register, the CPU is finished with the compare instruction, and it can then request the next instruction from RAM. Generally, the next instruction after a compare instruction is a jump if instruction. This combination of a compare and a jump if instruction, by the way, is very common in computer programming. Anytime there is more than one possible path through a program, the computer is using these instructions to tell it which way to go. So now that we're finished with the compare instruction and our flags are saved in the flags register, we need to tell RAM that we're ready for the next piece of data, in this case the next instruction. So inside the CPU, another register that is very important is what's called the instruction address register. The CPU uses this register to know where the next instruction should come from in RAM. When the CPU is ready for the next instruction, it enables the instruction address register onto the bus. Eventually, the instruction address will flow to RAM, but it doesn't get there directly. There is an intermediary register called the memory address register, whose only job is to tell RAM what memory address the CPU wants next, since it won't always be an instruction. Once the instruction address is set into the memory address register, it is automatically sent to RAM since the memory address register doesn't have an enable wire. The control unit then turns on the enable RAM wire, and RAM automatically sends back the data at that address, which in this case is an instruction. That instruction is then saved in the instruction register, and the control unit begins processing it. In this case, it's a jump if equal instruction, which checks to see if the equal flag is on. It does that by running one of its wires and the equal flag wire into an AND gate. If both inputs to the AND gate are on, then the output wire turns on as well. This output wire will then trigger the jump. That jump eventually retrieves the next piece of data from RAM, which happens to be an address, and move it into the instruction address register. When the jump if equal instruction is over, the CPU then processes the instruction at that new address. At that new address may be some instructions that output the text "you guessed correctly" onto the screen, because now we know that the user guessed correctly. So we'll add the final 4 wires to our CPU, which are used to control the external devices like the monitor and the keyboard. We now have a nearly complete picture of what the Scott CPU looks like. Data moves around inside the CPU using the bus and is stored in each register according to how that data is going to be used. Each instruction that we have seen can be processed by the Scott CPU in about 6 clock ticks. Modern CPUs can process multiple instructions per clock tick, meaning that the computer you're using to watch this video is likely processing tens or even hundreds of billions of instructions per second. That phenomenal speed is accomplished by using more than one of each component and making sure that all the components are active as much as possible. This makes modern CPUs much more complicated than the Scott CPU, but they are still fundamentally doing the same things as the Scott CPU. So now let's zoom back out and we can see all the wires that run back out to the pins on the chip. On the right are the set RAM and enable RAM wires. On the top are the RAM address wires. On the bottom are the data wires that run to both RAM and the external devices. And on the left are the input-output control wires. So let's zoom back out to see the rest of the chip, and we'll put the cover back on the CPU and put it back in the motherboard. Using the ports on the left, we can now plug in the cables that connect our monitor and our keyboard. Each of these ports has an address, and that port address is what the CPU uses with an in or an out instruction. That port address, by the way, is sent using the data bus, since the address bus in this computer is only used for RAM. So we'll zoom out to see how the motherboard fits inside the computer case. In the computer case is the last component we'll look at, which is the hard drive. As soon as the power to the computer is turned off, all the data in RAM is lost, so you have to have a way to store it more permanently. For that, we use a hard drive. Inside the hard drive is a spinning disk covered in tiny magnets with a small metal arm floating above it. The arm moves around to the different parts of the disk where different data can be stored and retrieved. The disk and the arm generally move very, very quickly, but nowhere near as fast as the CPU can process data. For this reason, all the data from the hard drive must first be moved to RAM before it can be processed. So we'll put the hard drive back inside the computer and zoom out. Here we can see the program we just ran and the message telling the user that he guessed correctly. So now you've seen the very basics of how a computer processes information. You'll find much more about the Scott CPU and the book at the website buthowdoitknow.com. Also, there are a few small differences between the book and the video, but those shouldn't detract from your understanding of either. You can find a list of these differences in the video description. Thanks for watching.